topic of this episode is Laplace's equation. So we shall start looking into interpretation of Laplace operator and Laplace's equation. And one of the interesting aspects of Laplace's operator is that it contains multiple variables like x and y that all describe separate dimensions in space, and that is opposed to what we saw so far. For example, when we studied the wave equation, we had an independent variable time and another independent variable x for the space, say, and those belong to different physical dimensions. But here we have two spatial coordinates, and that enables us to use different types of coordinates. For example, you could work in a rectangular domain. You could use Cartesian coordinates, but if you would study problems that have to do with circular or cylindrical geometries, you could use polar coordinates. So that is one of the things that we will focus on in the context of Laplace's operator. And as always, we will pay attention to boundary conditions, of course. But let's first look into what Laplace's equation is about and what it looks like. And maybe you better focus on the middle green box over here. That is by definition the definition of Laplace's equation. And I think it is easiest to read the right hand side first. It says we focus on some scalar field, and a scalar field is a field that takes a value at each point in the space. For example, the temperature distribution in a room would be an example of a scalar field. At each point in the room the temperature is defined. And the gradient of a temperature then is a vector field, so again at each point in the room you would have a vector, and that points in the direction of the strongest increase of that of the temperature in that example. So that would be the gradient, and then Laplace's equation says, well, the divergence of that gradient, that should be zero. So the scalar field should be such that the divergence of its gradient is zero. And that is a combined operation. It has so many applications that it has an abbreviation. This is written nabla squared. And if you look at it by itself, then it is defined as in this upper green box. So the nabla squared operator is also sometimes written as a delta. And it is defined as being first take the gradient and after that the divergence. You can also write like this. So first gradient, after that we take the divergence, and the combination of that is called Laplacian operator. Then the interpretation is actually straightforward. So in that context, that scalar that we are working with is often called potential. And we focus for the interpretation first on that gradient that is calculated. That is often called force field, and then a minus is added. And it is because in physics, in interpretation, we like to think of things going downhill. So the gradient would point uphill the value of that potential field, but things tend to move downhill, and that is why we add this minus sign. So minus the gradient is a vector that points in the direction of the strongest decrease of psi. And that vector field would be a force field, F being a vector field. And there's a note here that as it was defined in the calculus course, such fields that can be written as a gradient of some potential are called conservative, and you can easily prove or derive that if a field is a gradient field, then its curl is zero. That is actually something that we used when we studied the exact equations. So you could solve an equation of that form. If you could write the vector field that defines it as the gradient of some fields, some scalar field, and to test if that is possible, we use this curl-free condition over here in 2 dimensions in that case. So we've met this before, and then so that is the gradient, and then Laplace's equation furthermore requires that the potential is such that it is not only curl-free but also divergence-free. And then by Gauss's theorem, if a field is divergence-free, that means that the total flux of that field F in and out any selected volume in space, so the integral of that vector field over the surface enclosing that volume, that must be zero. So you could conceive it that F then is the velocity field of an incompressible fluid. So a fluid is going into some volume, and if it is not compressible, then it must come out somewhere else. And the total flux of the velocity of that fluid must be zero then. So that is a conceptual way to conceive the notion of a divergence-free field. And examples in physics furthermore are, for example, the gravitational field in a vacuum. It's actually the mass is the source of the gravitational field, and if there is no mass, then the vector field F, which is the gravitational force, should be divergence-free. And the gravitational force is also conservative, so it can be written as the gradient of some potential, and actually then it follows that the gravitational potential should obey Laplace's equation. And a similar reasoning holds for the electric field in electromagnetism. In the absence of charges, should also obey Laplace's equation. We also met Laplace's operator already when we derived the heat equation, applying the very same reasonings about gradients driving the heat flow. The gradient of the temperature drives the heat flow, so there was the gradient. And we said, well, the divergence of that heat flow, if that is non-zero at some point, then apparently the heat content of a volume element about that point changes, and that is this derivative with respect to time then, because the heat content was assumed to be proportional to the temperature, and in that way this time derivative of the temperature distribution became proportional to the Laplace operator acting on the temperature distribution. But you could go back to the lecture on the introduction of the heat equation for the details. But we did meet the Laplace operator then. And so you can also think of solutions of Laplace's equation as describing equilibrium states of a field that is subject to, for example, diffusion-like dynamics. Because stationary equilibrium here means time independence, so the derivative with respect to time will be zero, and then again you are left with the Laplace's equation. So you could interpret it as being describing a temperature distribution in equilibrium given, for example, some boundary conditions. So that would be one interpretation that you could give to exercises that we will meet. Well, what does Laplace's operator then look like in various coordinate systems. Well, if you would have Cartesian coordinates in the two dimensions, you would have x and y, and then the gradient operator is like a vector operator. It has two components, and the first component is the partial derivative with respect to x, and the second is the partial derivative with respect to y. So the gradient of a field u, for example, would be the partial derivative of u with respect to x, and then the second component, the partial derivative of u with respect to y. And if I would take the divergence of that, I would take a dot product with this same operator again, so you get t dx squared of u plus t dy squared of u. And this then is the representation of Laplace's operator in Cartesian coordinates. You could write it with the subscript notation u xx, two subscripts, and u yy, two subscripts. So twice the derivative with respect to x and twice the derivative with respect to y. As said, you could also think about other coordinate systems, because the interesting thing, once again, is we have here two independent variables, x and y, and both have to do with space. So that is the difference between Laplace's equation here and, for example, the wave equation that we met before. Now we had time and x as coordinates, and we did have pictures of the xt plane, but if you would think about, for example, triangles, if you would draw a triangle in the xt plane, that wouldn't actually make much sense, because one direction, the length of the side of a triangle would be in meters, and in the other direction it would be in seconds. So what then would be the length of the unit of the length of the diagonal side? So xt plane is easy to conceive, to get an overview of problems like how do we specify boundary conditions, but it is not really a geometrical plane in the sense that you would draw geometrical figures in that. So what would be the meaning of a circle in the xt plane, for example? But here it is different. So we have now two coordinates, again, x and y, and both are coordinates of a spatial, of a geometrical space, you might say, because in such a space you can draw triangles, and the geometry of triangles holds, and a circular domain does make sense. So now it makes sense to have polar coordinates, for example. So you would have a radius and an angle. We will come back to that later. But you would have a radius and an angular coordinate, and that relates to the Cartesian coordinates, like this overview in this lower green box over here. So x would be r times the cosine of your angular coordinate, and y r times the radius times the sine of the angular coordinate. So I have then an alternative way to coordinatize a plane, and with that comes an alternative way to represent that same Laplace operator. So that and that would then look like this. Now, how to do that is actually an exercise that was done in the calculus courses by taking partial derivatives and applying the chain rules for that. So in that sense it would be a straightforward exercise, given this definition, for example, of the Laplace operator, this definition of the Laplace operator, to calculate what would be the recipe that you would have to apply if you were given that same function, but now described in terms of polar coordinates. Now, and that is in the lower green box over there. So the Laplace operator can be given in various coordinate systems, and in each of those coordinate systems you can study the solution of the Laplace equation, which is what you get if you set this equal to 0. Well, now given the applications for Laplace's equation, say if we would think about the temperature of some rectangular domain down here, and if this would be some body, we could conceive that we would cool it with iced water from 3 sides, and maybe heat it from a prescribed temperature, so expose it to some temperature reservoir from another side. So we would have the Dirichlet conditions again, prescribing the value of the unknown variable, which is could be a temperature distribution u here, but we would prescribe it at all sides of the domain. So that is again different from what we did for example, the wave equation, which was also second order in both of its coordinates. But then we chose to have boundary conditions on 2 sides and 2 initial conditions on one side, and one side was left open to infinity, for example. But here it's different, given the applications for Laplace's equation, it is common to describe boundary conditions surrounding a domain. Now and then again, because the differential equation here is second order in all of its dimensions, it is natural to expect that you might prescribe one condition on each side of the domain. So in this example we would prescribe homogeneous boundary conditions on 3 sides, and on one side we would prescribe the function that u should have as a function of the coordinate y, which is the vertical coordinate here. And so you might expect that it is possible to describe such conditions, and that Laplace's equation then indeed would have a solution. And that is indeed the case on a rather liberal conditions. One practical remark here: if you solve Laplace's equation on rectangular domains, in practice it is easiest, as we will see, to keep the boundary conditions homogeneous on all sides except one. But we will come back to that. So we shall study a problem of this form first as an example in the upcoming slides in a minute. But here's an advice of what to do if there would be more than one side non-homogeneous. Then the advice is to break up the problem and into problems that are homogeneous on 3 sides except one, solve those, and then superimpose all those problems and their solutions to make a non-homogeneous problem that is non-homogeneous on the multiple sides. But the textbook provides some exercises and examples of that, but that would then be the general strategy. So this is the basic problem for Laplace's equation on a homogeneous domain, on a finite domain, 3 homogeneous conditions and 1 non-homogeneous condition. Yeah, and then again also in this context we can prescribe values, and then you would have Dirichlet problems. That would be, as we just had in the previous slide, we prescribe temperatures on the boundaries of a domain, for example. But you could also prescribe gradients, a Neumann problem. That is the case if you would say, well, one of the sides of a box is insulated. Another application would be if you study irrotational incompressible fluid flow confined by boundaries. And you would say, well, there's no flow into the walls. If there's a fluid in a container, there's no flow in the wall, so the perpendicular component of the gradient to the stream potential should be zero, because that gradient in that application denotes the velocity, and there should be no velocity component perpendicular to the walls. So that is again an example of a Neumann boundary condition that you would have. Now, existence and uniqueness of the solutions for Laplace's equation under these boundary conditions can be shown, provided that the shape of the boundary and the functions that appear in it satisfy certain very mild requirements. But the details of that are actually outside the scope of the textbook and this course. But as we shall see, a rectangular box is already non-differentiable, and that is no problem with Laplace's equation, as we shall see. So in that sense, the conditions are mild. There's no smoothness conditions for the boundaries, for example. So let's have a look at what solutions and the problem of solving Laplace's equation on a rectangular domain, so Cartesian coordinates looks like. So we shall study a Dirichlet problem for a rectangle. So we consider the following problem on a rectangle, sketched in the graphics in the lower half of the slide. So maybe that is the easiest. So in the interior of a rectangular domain, we look for a function u that obeys Laplace's equation. And then we shall describe homogeneous Dirichlet conditions on all sides except one, and that exception is over here. For x taking the value a, this vertical side, there we prescribe that u of x and y, for x taking the value a, so along this side takes a prescribed value, and that is that function f of y, because y is the vertical coordinate in this plane here. And then at all the other sides, for example, the top side is described by y taking the value b. So for u of x and y, with y taking the value b, there we prescribe, in this case, a homogeneous boundary condition, so u should be 0 over there. And in that same way we can prescribe homogeneous boundary conditions on all those three sides of that rectangular domain. And all that is also gathered in this box over there. And we emphasize that in one direction we have homogeneous boundary conditions. And those deserve extra attention, because it is usually easiest to bring in those first, to take advantage of those first. That is because in general homogeneous boundary conditions have the advantage that if you apply superposition, as we will do, because again Laplace's equation is a linear equation, so again we will have the plan to first look for separable solutions, so as to find the fundamental set of solutions, and then apply superposition to form more general solutions, and then proceed. Now, and then if you have that plan in mind, the homogeneous boundary conditions are promising, because if you do superposition, you at the boundaries you add zeros to 0. If you have separable fundamental solutions that already obey those homogeneous boundary conditions. So here we have homogeneous boundary conditions on these opposite sides. So that is apparently the direction to concentrate on the first, looking for factors obeying homogeneous boundary conditions. So again, we shall look for solutions of separable form with a plan in mind again. Once we have those, we will superimpose them. But we start looking for separable solutions in the first place. We substitute them in the Laplace's equations, so we have the double derivative with respect to x here, that only acts on the function x of x, and this then is to be considered a constant, so it is just there, and we get x double prime as the effect of these two derivatives with respect to x acting. And here, if we substitute x times y here, we get the 2 primes for the function y, and x of x is now to be considered a constant, so that remains as a prefactor. Now, if you would separate, bring one term to the other side, and divide by x times y, you end up with the conclusion that x double divided by x should equal minus y double divided by y, one function being only a function of x, the other function being only a function of y, and those two can only be equal to one another if both functions are equal to a constant function actually, and those constants must be the same. So briefly, that can be written like this, and once again you end up with two eigenvalue problems that are coupled because their eigenvalues are related. And given all the experience that we have now with this, because it is rather the same with the heat equation or the wave equations, this time I chose a simpler notation for the separation constant, so that actually with respect to this equation it would really correspond to the usual notation for eigenvalues. But note that there is a sign difference, and also the standard form for an eigenvalue problem would be to write this at the other side, but it is of course equivalent to the equations that are in the green box here. So given all the routine that we have now, we might as well write it like this. So lambda is the separation constant, and it is as well the eigenvalue with respect to the first equation. Now concentrate on the boundary conditions as we always did, because bringing in the boundary conditions helps us to select eigenfunctions. And as I already remarked, if you look at the problem, we have two homogeneous boundary conditions at opposite sides. So opposite sides over here and over here. So we have homogeneous boundary conditions on the function y, actually, the factor that depends on the coordinate y. And then the general advice is to proceed with those first. So first solve the eigenvalue problem for the function y, because once again when you superimpose those solutions, then you will add zeros to zeros at those two sides, and then you end up with a series solution that still satisfies those homogeneous boundary conditions. So that is the tactics that we have in mind. So we concentrate on the function, on the equation for the y that we had, that is this one, combined with these two homogeneous boundary conditions. Yeah, and then immediately we recognize that if we would like to have eigenfunctions of such an equation, such that at two opposite sides you satisfy homogeneous boundary conditions, then again, if you would use the table, you end up with the conclusion that y must be sine functions, because the sine function again is 0 for y is 0. And at the other side, which is y is b, you can also have it equal to 0 as long as the prefactor of y is n pi over b. So that's actually quite the same type of problem that we solved already for the heat equation, and also for the wave equation for the string, when we also had two homogeneous boundary conditions at the opposite sides of the domain. So once again, we find the sine functions as eigenfunctions, and now lambda is known. Lambda is is minus the eigenvalues here, so lambda is positive, and it is equal to n squared pi squared over b squared, if you substitute that to calculate. So lambda is known, and now we can go after solutions for x of x from the first equation, using those values of lambda. And lambda is positive, and there's a minus sign here, so you could get exponential functions as solutions, or the even and the odd parts of those. So you would have increasing and decreasing exponential functions at the even and the odd parts of those, or the cosine, hyperbolic cosine and hyperbolic sine functions, and those equally well span the linear space of all linear combinations of those exponential functions. And this is actually a convenient way to write the general solution of this equation for x of x. And why is that? So that is very similar to the general solution that you would have for this. The general solution for the equation for y is the linear combination of all the cosines and all the sines. So a linear combination for cosines and sines. And here, because of this minus sign, the general solution for x of x is a linear combination of hyperbolic cosines and hyperbolic sines. And why is that convenient? Well, if you now apply that second boundary condition, that homogeneous boundary condition for in the x direction, which is over here, which says u of 0 should be 0 for all y, so that implies here that x of 0 should be 0. If you combine that with this general form, x of 0 should be 0, then the hyperbolic sine of 0 is 0, and that immediately implies that k1 here must be 0. So the general solution for x of x satisfying this equation And the homogeneous boundary condition at one side of the domain is really that x of x should be hyperbolic sine functions. If somehow you don't like hyperbolic functions and you just work with the exponential functions, you also find this, by the way. And you should write the general solution of this equation for x of x as the weighted sum of increasing and decreasing exponential functions, and then by the same argument applying the boundary condition that x is 0 and that it should be 0 there, then you will also find that that the general solutions of this equation satisfying that boundary condition is exactly this. Find exactly that the odd part, so the difference of two exponential functions with the same weight coefficient, with the same amplitude, the same weight coefficients should be the solution then. And so we arrive at the conclusion that our fundamental solutions, the products of functions of x and y, are actually of this form now. So we have a sine function in the y direction and a hyperbolic sine function in the x direction. And again, we superimpose all those separable solutions, the fundamental solutions, in a big series. And again, we start summing at n is 1, because we have signs again here, so n is 0 doesn't add any non-trivial solution, that we just render 0, and the negative integers would give the same as the positive ones, except for a minus sign, but those are then not linearly independent. So again, we form a linear superposition of all these fundamental solutions, each with their own weight coefficients, and that is then the most general solution that we can form from these fundamental solutions. And so we have again these arbitrary constants in the summation, but we can still adjust, and that you can use to match boundary condition number 4, the non-homogeneous one. So the remaining non-homogeneous boundary condition, that was over here at the fourth wall of the boundary, that can be met by adjusting the coefficients. And so here it is. This is a copy of the most general solution that we could form so far. Here's our boundary condition for all y between 0 and b, and for x equal to a over here, the prescribed value of u at that boundary is a prescribed function of f. So if you combine that, this prescribed value, and then for x substitute a into the solution as we have it, you get this. So that's again a sine series. The only difference between the sine series that we had in the heat equation is that this time the coefficients of it are not just our unknown superposition constants Cn, but there's also this hyperbolic sine function. But actually that is a known constant. If you know n, and this is just a known number, it only depends on n, pi, and the length of the sides of the domain. So in practice those numbers are known, it's not an unknown. So what does happen if you now can say, well, I have a sine series, so I can apply the orthogonality of the sines to calculate coefficients, then what you do calculate is actually this combination. So what you do get is Cn times the hyperbolic sine of n pi a over b. That is now equal to the integral of the target function times that sine, integrated over the length of the domain. We're integrating in the direction of y, so that will be from 0 to b, and divide by half the length of the domain. And that would give you the coefficients of the sine series, but once again, that coefficient of the sine series is this combination now. So that is what I write. And then the next step is easy, I just divide by these numbers. And none of those are zero, by the way, because it would be zero for n is zero, but that is excluded, and the hyperbolic sine has no further zeros, so it is safe to divide. So you just divide by this hyperbolic sine to calculate the Cn. So you see, it looks different, but the reasoning behind this procedure is exactly the same as that we had in earlier cases. You meet the sine series and you apply the orthogonality of the sines, and hence the idea of having an inner product and an orthogonal basis to calculate the coefficients by projection. And the only thing that you have to be aware of is that the coefficients of that series actually now this combination, and not just the unknown c's that we are really after. It is this combination then that you get, that you calculate if you apply the orthogonality relation. So there's one more simple step to actually calculate those c's. I could quickly have an example, which is just basically substitute some numerical values for into a solution that we just derived. And furthermore, there's a function specified here, so the function f of y along this that describes, let's say, the temperature along this wall is given by this triangular shape here. So it would be y until y is 1, and then 2 minus y between 1 and 2 over here. And furthermore, it is prescribed that one side of that rectangular domain has the length 3 and the other side has the length 2. So you can substitute 3 and 2 for those a and b in the solution and work it out. And if you work out the details, this is what you get. And the idea is just to have a kind of a plot of what such solutions of Laplace equation look like. Well, they are. So here apparently is that prescription of the temperature, that as we had in the graph over here, it starts from 0 to 1 and then back to 0 again along that far side of rectangular domain. So here it is, it starts from 0, increasing to 1 and then decreases to 0 again, and alongside all the other walls we keep it 0. And then a temperature distribution, say inside the domain, would look like this, so real smooth. And then the right hand side, an attempt has been made to make a kind of a three-dimensional plot of that. So the height here, the vertical axis, would be the temperature axis. And the x and the y spatial directions are plotted as the ground plane of that three-dimensional view. And the temperature is hanging there like a kind of a tent. And so with that, we have completed looking into how to interpret and how to solve Laplace's equation on a rectangular domain in Cartesian coordinates. And this then is actually a good moment to now first do exercises with the Laplace's equation in Cartesian coordinates. So, and then in a separate episode we will pay attention to how to deal with this equation in polar coordinates and the peculiar details of handling such problems. So now that we have reached that point, we call this an episode.